Compound inequalities. These need a little more attention, so we're only going to study this one topic, one section here. You have run into these before, so again, this is review. We're going to solve and graph conjunctions, con. For those of you taking Latin, you have an idea what that means, right? It's got something to do with joining, doesn't it? And solve and graph disjunctions, which have something to do with separation. Let's graph the following. This is pretty simple for us. This is a little 5-minute review. It may take us a little less or a little more. X less than or equal to 1. So the thing to focus on here is we have a boundary at 1. So let's find that. That's going to be right here. Now, it says x could be equal to 1. So that tells me when I locate this boundary right here, it's going to include the boundary. It's equal to it or less than. This tells me I'm going this way. X is less than 2. So my boundary, let me grab one of these. My, boundary is at 2. It does not equal 2, so I'm going to leave this an open circle, and it's less than 2. So we're all x's in this direction on to negative infinity. This one we have to solve before we can graph it. What does that mean? It means we have to get this x all by itself. All right, we'll try solving it. We're going to use almost the same rules that we use for equations. As long as we do the same thing to both sides, we're going to be good with an inequality. So I'm going to add 3 to both sides. So this will become a negative 4x. When I add 3 to this side, we get a 0. When I add 3 to this side, I get negative 8. As long as I divide both sides by the same value, they will stay true. However, when it's a negative, this is the big difference. When it's a negative, as it is here, we're going to have to reverse the sign. So instead of being less than, it's going to be greater than. I'm going to divide both sides by a negative 4, giving me x. And I divide a negative 8 by a negative 4, I get a positive 2. So I have x is greater than 2. My boundary is at 2. I'm going to draw that first. It's my boundary. Is it going to be an open dot? Yes, because the boundary is not included. It's everything greater than 2, but it does not include 2. So there's my solution for that one. How about this one? Well, I could start by dividing everything through by 2, couldn't I? And it's a positive 2, so it's not going to reverse my symbol. So I'll have 1 minus x is greater than, symbol is staying the same, 3 over 2. What do I do now? Well, remember I'm trying to isolate x. So my next step, I'm going to subtract 1 from both sides, so I'll have a negative x greater than or equal to 3 over 2 minus 1. Now I'm not going to write 1, I'm going to write 2 over 2. And of course you know why I'm doing that, don't you? This is equivalent to 1, but this gives me a common denominator so that I can simplify this into negative x is greater than or equal to 1/2, right? If I have 3 halves and I subtract 2 of them, I'm left with only 1. half. Now, I'm not there yet because I don't want to know what negative x is. I want to know what x is. Now I have to divide both sides by -1. So this negative, dividing or multiplying by a negative, has a big impact here. I have to reverse my sign. So I will have x is now less than or equal to, when I divide this by a -1, I get a positive 1/2. So where is positive 1/2? Well, it's going to be right between 0 and 1, isn't it? So I'm going to draw my boundary right here. Oh, and it includes the boundary this time. See that? It can be equal to the boundary. So I fill it in, and it's less than. So I'm going in this direction. Okay? Compound inequalities. We're going to look at the conjunction first. The conjunction uses the logical and. Something and something else. So, the sun is shining. That's one condition. And rain is falling. Now, this can happen, can't it? It is possible that the sun is shining and at the same time rain is falling. This is called rainbow territory, isn't it? This would be an example of a conjunction. Both of these must be happening for this statement to be true. When we talk about inequalities, we use the same logic. We're going to start with graphing the first one, and I'll do it in green so we can keep track of things. X is less than or equal to 5. So my boundary point is at 5. We've got equal to, so I'm going to fill it in. We're going to include that boundary. And everything less than that. So this all by itself is true up to and including 5 and on to negative infinity. This one, less than -3. So -3 is my boundary. Does not include -3. So I'm going to leave that circle open. And here is where this one is true. So, can this be true? And if it is, where is it true? Well, first place it's true is just beyond -3. So this is where the conjunction is true, right here. Why is that so? Well, of course I didn't draw this all the way, but we know that that goes on to negative infinity. So the only place that these are both true, this one and this one, is right here. Okay? That's a conjunction. We have another type of compound statement that we'll talk about in just a minute. Can the following conjunction be true? X greater than or equal to 3. Okay, let's find our boundary. It's equal to, so I'm going to fill it in, and everything greater than. X less than or equal to -1. So my boundary is at -1. Again, it's equal to the boundary, and everything less than. Okay. Oh, I meant to do that in red. Put this into a different color to be consistent. All right. So I wanted to graph it down here, actually. And then where would these both be true? I'll do that in blue. They don't overlap at all. So where do we have both this true and that true? Nowhere. Can it be true? No. This is a false conjunction. The intersection of these two solution sets does not exist. We could also say it is empty, or still another way to say it, it is null, and there's a symbol for null, which is very different from zero. Null means there's nothing there. It's worse than zero. Nothing is not zero in mathematics. Zero actually represents a point, a place, a value, where null means it is totally empty. What is the intersection of these two sets? Well, let's see what we can come up with for this one. We've got greater than or equal to 3, so I'm going to be going in this direction, and I'm going to be using a solid dot, which will be placed at 3. This one, x is less than 5, I'm going to be using an open dot, and I'm going to go in the negative direction when I'm less than, and that's going to happen at this point. So what is my graph going to look like? I'm just going to grab a highlighter. It's going to be from here to here and including this. That's going to be the intersection of those two sets. That is where my conjunction is true. So how am I going to write this? I'm going to write it as x being less than 5 and greater than. Now notice I'm looking at x on the greater side, so x greater than or equal to 3. Let's keep going. We're going to graph this one. I've got two boundaries. Let's graph the boundaries first. Both of them will be open circles, won't they? So I've got x greater than 2. So x greater than 2, and I want an open circle. X greater than 2. And I've got x less than 5, another open circle. Very similar to the one I just did, isn't it? The inequality is really a conjunction of these two statements, and graphically it's from here to here, not including the boundary point. The solution set is the intersection of the solution sets for each of the separate statements. And it could be written in set notation like this. This sign here means intersection. Intersection. Right there. Whoop. Wants to make a straight line out of it. This statement here, x such that, we would read the straight line as such that x is greater than 2. And this one we would read as the set of all x such that x is less than 5. Now we're going to solve a compound inequality. We want to get this x all by itself. Let's see what we have to do. We know we've got this part is true just from the first two members of this. We can no longer say side because this actually has 3 parts to it. We'll call them members. And the middle and the last are another statement which is also true. So we could solve these as separate statements. What are we doing? We add 5 to both sides. Add 5 to both sides. We get x is greater than 2 and x is less than 3. Let me do it over here, doing all of them at the same time. I'm going to add 5 to both sides. See, I can't get away from saying it. I mean to all three members, which gives me 8, which is less than 4x, and this zeros, less than, this should have been 12. Then when we divide everything through by 4, we get 2. X is greater than 2 and less than 3. So how would this graph? We're going to use the open set here. Find 2, and x is greater than that but does not include that, and 3. So when I graph this, it's just from here to here. Solution set is all x such that x is greater than 2 and x is less than 3. Compound inequalities. We're now going to move from conjunctions to disjunctions. Now we're going to say the sun is shining or rain is falling. So this statement is true even if rain is not falling, as long as the sun is shining, and vice versa. So as long as one of those is true, the whole statement is true. For a disjunction to be true, at least one of the statements must be true. For a conjunction to be true, they both have to be true at the same time. This represents an intersection. Where do they intersect? This represents a union. We add them both together. Now, logically, when we think add, we don't think or, do we? But in conjunctions and disjunctions, the intersection, where they both have to be true, is the and. The union, where either one of them can be true, is the or. Compound inequality, let's try this. If x is less than 2, so which one do I want? I want this one, open circle, or x is greater than 1, x is greater than 1. Can x equal 44? Well, let's see. So we know with the or, that's the important piece here, we've got an or, so we've got a disjunction, means that all of this is true and all of this is true. In other words, there's no number that isn't true in this case. Wow. How about this one? If x is greater than 2, so again we're going to have an open circle, or x is less than 2, so we're right here. So we're going to look at the full solution set. It's everything from here to positive infinity and everything from here to negative infinity. So, can x equal 2? No, that's the only point that didn't get covered by one or the other. So let's try graphing this. X greater than 2 or less than 5. Okay, greater than, and not including would be this one. Greater than 2. Or x is less than 5. X is less than 5. This is an or. We're not looking for the intersection, we're looking for the full union. So let's see what that will include. That would be all of this, not including that boundary, and all of this. So is there any number that isn't included here? They are all included. Now we're going to solve the next one. Whew, this is a disjunction because it's got the or. Let me see, I'm going to add 2 to both sides. 3x less than 6, and then I'll divide by 3, so x is less than 2. The other inequality, I'm going to divide everything through by 2. I'll have x is greater than 5. So let's try graphing that one. In this one, just like above, I am not including the boundary point. X is less than 2, so my boundary point's at 2 and I don't include it. Use the open circle. X is greater than 5. Alright. So let's figure out where this is true overall. Well, it's true from 2 and below, and true up here. Because if either one of them is true, this statement, because it's an or statements, disjunction, which is a union. So we've solved that. Let's look at this. The solution set is x such that x is less than 2 here, or x is greater than 5. And that's it for today. Let me get out a interesting pen. How about this? See you back in class.